Hi everyone. In the last video, we learned something about diagonalization and saw a simple example of a 2x2 matrix getting diagonalized. In this video, I want to show you a harder example and look at diagonalizing a 3x3 matrix and what kinds of things we can see more generally when we're working with eigenvalues and eigenvectors of higher dimensional matrices. So the matrix is bigger than the 2x2 that we saw in the last example, but the steps for finding the diagonalization are still the same. So step 1 is find the eigenvalues. Step 2 is to find corresponding eigenvectors, remembering that they have to be linearly independent. So we have 3 linearly independent eigenvectors as the columns of P, and the eigenvalues as the diagonal entries of our similar matrix. So we're looking for P times D times P inverse. All right, so let's start by finding the eigenvalues. To find the eigenvalues, we're going to set up the determinant of A minus lambda I and set it equal to 0 and solve. That means we're going to be finding the determinant of the matrix 1 minus lambda, 3, 0, 3, 1 minus lambda, 0, and 0, 0, minus 2 minus lambda. And setting that equal to 0. Let's see, since the third row or third column are mostly zeros, I'm going to use cofactor expansion along that. You can calculate the determinant any way you like, though. So this determinant is negative 2 minus lambda times 1 minus lambda squared minus 9. And if we multiply this out and simplify a little bit, you'll see that this is actually equal to lambda plus 2 squared times lambda minus 4. It's actually not a hard one. Even though it's a cubic polynomial, it's not a hard one to factor. So we're setting this equal to 0, so that means we have 2 distinct eigenvalues. I'll call lambda 1 4, and then we have lambda 2 is negative 2, but it occurs repeatedly. There are 2 factors of that characteristic polynomial that have root 2. So I'll just denote that by writing multiplicity 2. Now we need to find the associated eigenvectors. So we move on to step 2. So we'll start with lambda 1 equal to 4 and set up the homogeneous system that we need to solve. So we're going to have A minus 4 times I times our eigenvector v1 equal to the 0 vector. And if we plug in lambda equals 4 into our equation, we'll get negative 3, 3, 0, 3 minus 3, 0, and 0, 0, minus 6 times eigenvector v1 is equal to the 0 vector. And if we do one row reduction operation, say row 2 plus row 1, that is going to give us the system that looks like negative 3, 3, 0, 0, 0, 0, and 0, 0, minus 6. Again, with our eigenvector v1 equal to 0. And I can already see what the solution of this linear system is going to be. So the general solution is this, right? x3 is going to have to be equal to 0, and x1 is going to have to be equal to x2, and x2 is free. So if I write that all together as a vector, my first eigenvector, x1 and x2 have to be the same, x3 has to be 0. The simplest vector I can think of that has that property is 1, 1, 0, and so I'll use that. Remember that, again, with the eigenvectors, all we need is one vector that points in that direction of the general solution. So it doesn't matter which one we pick, it just has to satisfy this criteria. So I'm going to take v1 equal to 1, 1, 0. So now moving on and working with our other eigenvalue, which is negative 2 and has multiplicity 2, So I'm writing here actually that lambda 2 and lambda 3 are both negative 2. And now we got to see what we're going to get. So if I compute now a minus negative 2i times v2 or v3 equals 0, the matrix I'm going to get is 3, 3, 0, 3, 3, 0, and 0, 0, 0. So you can see that if we did one row operation of row 2 minus row 1, we would have just 3, 3, 0, and all of the rest of the matrix would be zeros. So x1 has to be equal to negative x2, but x2 and x3 are both free. So now we have these kind of two different parameters that we can play with, right? In this case, we just had one free variable x2 and plugged in a 1 for that in order to determine a whole fixed vector. In this case, with lambda equals negative 2, we have two free variables. So let's just write down the general solution first. So the general solution looks like minus x2, x2, x3. So we need two linearly independent vectors that satisfy that. And that's pretty easy to do. For my first eigenvector, I would set x3 equal to 0 and x2 equal to 1. So that would be minus 1, 1, 0. And for the second one, I would set x2 equal to 0 and x3 equal to 1. So 0, 0, 1. And now, with these three vectors, which are readily seen to be linearly independent, and these three eigenvalues, we can write down our diagonalization. Our original matrix was this, and we found the diagonal matrix D that has the eigenvalues of A along the diagonal, and then our P matrix is going to be the matrix, the columns of which are the eigenvectors that correspond to the eigenvalues as they appear in the diagonal matrix. If we wish, we can compute P inverse. It shouldn't be too bad. There it is. And so we can write down our decomposition. And we're done.